Standing on the shoulders of giants, from ML to ML. If I have seen further, it is by standing on the shoulders of giants. This famous line from Isaac Newton captures a timeless truth about scientific progress. Newton himself became one of those giants. His laws of motion and gravitation shaped physics for centuries. Later pioneers like Albert Einstein and Niels Bohr, while challenging and refining Newton's ideas, still had to deeply understand his work to move forward. Einstein's theory of relativity built on and ultimately expanded Newtonian mechanics. Bohr's quantum theories emerged in contrast to the predictability of the Newtonian world. In much the same way, today's data scientists and AI researchers can see further because they are standing on the shoulders of the great statisticians who came before them. Figures like Ronald Fisher, the British pioneer who introduced the method of maximum likelihood, ML. That foundational idea continues to influence how we model, estimate, and build modern machine learning, also ML. If you've ever built a linear regression model or estimated a logistic regression in your work, you've already used one of the most powerful ideas that connects classical statistics with modern machine learning: maximum likelihood. While machine learning may sound like something completely new or technical, many of its core ideas are actually built on statistical concepts you're already familiar with, just dressed in new clothes and scaled up for modern data challenges. At its heart, maximum likelihood is about finding the model that makes the data you actually observed most probable. Imagine you have a data set and you hypothesize that it was generated by a specific type of probability distribution, such as a normal distribution or a Bernoulli distribution. This distribution has some unknown parameters, like the mean and variance for a normal distribution, or the probability of success for a Bernoulli distribution. The maximum likelihood method provides a principled way to estimate these unknown parameters from your observed data. It works by considering the likelihood function. This function quantifies how plausible it is that your observed data came from the hypothesized distribution for a given set of parameter values. Take predicting voter turnout as an example. You have data on thousands of people, and you suspect things like age, income, and past voting history play a role. When you use maximum likelihood, you're essentially asking, if my model is correct, how likely is it that I would see this exact pattern of turnout across all these individuals? You then tweak the model's parameters, like how much weight to give to income or education, until you find the version that makes your real-world data most plausible. It's a bit like fitting puzzle pieces together until the picture makes the most sense. The same logic applies to predicting whether a customer will make a purchase. Suppose you work for a retail company and you want to model how product views, email clicks, and prior purchases influence whether a user completes a transaction. A maximum likelihood approach tests different versions of your model, maybe giving more or less emphasis to email engagement or past purchases, and picks the one where the predicted outcomes most closely match the actual buying patterns in your data. In essence, maximum likelihood is a tool for learning from data. It doesn't just give you estimates, it gives you the best estimates under your assumptions, the ones that make your model align as closely as possible with reality. And this idea of tuning a model to best explain observed data is the same principle that drives many machine learning algorithms today. Now, let's jump into the world of machine learning. Take a basic neural network, a model often used in image recognition, recommendation systems, or language processing. When a neural network learns, it's adjusting its internal parameters, which is similar to weights in regression, to minimize the difference between its predictions and the actual outcomes. While the optimization in neural networks is typically done using gradient descent on a loss function, the choice of loss function, like cross-entropy for classification or mean squared error for regression, is often motivated by maximum likelihood estimation under certain probabilistic interpretations of the model's output. So why does it seem like machine learning is so different? Largely because of scale and flexibility. Machine learning models are designed to handle massive data sets with many variables, often with nonlinear relationships that are hard to model explicitly. And instead of focusing on statistical significance or confidence intervals, machine learning models are evaluated by how accurately they can predict new, unseen data. But under the hood, the learning process often still follows the logic of likelihood. In addition, unlike the maximum likelihood method, many machine learning methods, especially those termed non-parametric, deliberately avoid making strong assumptions about the underlying probability distribution of the data. Algorithms like decision trees, support vector machines, and k-nearest neighbors don't assume your data follows a specific form like a normal or Poisson distribution. For those trained in classical statistics, this connection is encouraging. It means you don't need to start from scratch to understand machine learning. In fact, your knowledge of model fitting, residuals, and goodness of fit gives you a strong foundation. The difference is mostly in the tools and the scale, not in the logic. Machine learning hasn't replaced classical statistics. Rather, it has built upon it. The core principles of how we fit models, make inferences, and draw conclusions are more similar than they are different. Understanding this continuity helps bridge the gap between disciplines and makes it easier to bring the power of machine learning into areas like business, public policy, and the social sciences, where thoughtful modeling is just as important as ever. Are you ready to take the next step beyond classical statistics and explore the world of data science and machine learning? I invite you to keep an open mind. These fields are full of powerful ideas and exciting advancements that build on the foundation you already have. Right now, you're standing on the shoulders of giants. And who knows, one day, others might be standing on your shoulders. What do you think? I'd love to hear from you. Please leave your comments here. If you found this video helpful, feel free to like, share, and subscribe. Let's keep learning and growing together.